Okay, so as you're copying the next part, I just want to kind of summarize what you're taking a look at. So if you are given a power series and it's centered at A, all right, you can do a few different things with it. You can find its derivative. So what you're going to see is affected by doing the derivative is just essentially that you're taking the expression with x in it and you're multiplying it by your constant and you're subtracting one from your exponent. So it's nothing different than we've done before. Okay. And it looks very similar to, taking the derivative. So now you're probably copying down here, okay, about its convergence. So we need to be able to do this for series that are convergent, okay? And what we're doing in the next one is we're integrating, okay, just like we would if we see an integral sign. So we're adding 1 to our exponent. We're dividing by our new exponent. So if you take a look at what's done in each of these terms, okay, it's the same thing. And we're doing it for where it's like x minus a once again. All right, that's what helps us find our radius of convergence and interval of convergence. So super duper important when it comes to power series. Okay, so we can actually put in the word power into our AM as well, but that's okay. We can leave it as just plain old series. That works too. So I'm giving you another moment or two to finish writing out the last sentence. Hopefully you're just down to the last sentence. Okay, so let me pull this off. In the meantime, maybe I can pull this off. All right. And I'm just going to move this up. There we go. So that way we can maybe see our example. Okay, so if you didn't copy that last sentence and you still are, that's okay. I'm just going to indicate, hey, we need to find f of x, we need to find f prime of x, and we need to be able to integrate f of x with respect to x. So if you look to see how f of x is described, it's an infinite series. Okay, so taking the derivative or integrating it is going to be new things for you to do. And actually the last things for you to do in this unit and in this course. So I'm glad it's actually something that you've done in previous units. These are like 2 of the 3 big ideas here. You have to know limits, you have to know taking a derivative, and you need to know how to integrate. So bam, we have that. And we actually did a lot of limits in this unit too, so it's really, really cool that we got to really cover a lot of the big ideas throughout our course. And let's go to our example. Okay, so I already went through, we're going to need the derivative and we're going to need to integrate, but we also need to find the integral of convergence for f. And f is over here. I'm sorry, kind of broke off. There's the sum should be negative 1 to the n power times x minus 2 to the nth power. Sorry about that. That's a typo. I hope I remember to go back in the slide and fix that. Over n, again from n equals 1 to infinity. So just make sure you correct that n. Let me just kind of stress that. Okay, so to find the interval of convergence, okay, remember we're going to need to check endpoints, so do that as well after your ratio test. So let's start our ratio test. So we have the limit of the absolute value of a sub n plus 1. This is going to be a sub n, so be careful with the n plus 1s. Wherever you see an n, put an n plus 1, especially after you correct that. Over a sub n, so just the way we corrected it. I would say the way it's written, but in this case the way we corrected it as n approaches infinity. Alright, so to do this limit, we're going to need to simplify our complex fraction. Okay, so I'm going to order these such that I can read them a little bit better. Okay, when we do keep, change, flip, this is going to happen. And the n plus 1 still in the denominator, the n flips up to the numerator. Okay, so what do we have here? We have the limit of -1, and this is going to be a quantity of x minus 2. Okay, looks like just that. And yeah, we have n over n plus 1. We're not going to really be able to simplify that, but don't worry with the limit. Okay, so absolute value of -1 is just going to be 1. Okay, so 1 times anything is itself. And we're treating x minus 2 as a constant. So, and we also don't need the absolute value here for our limit. If we do the limit of this expression here, it's going to be 1. The degrees are the same, divide the leading coefficients. So we end up, and I should have pulled out, there's an absolute value here. I tend to lose symbols. Okay, so we have the absolute value of x minus 2. I didn't need it over here, okay, because this is going to end up being positive, this limit of 1. If you want, you can write it like that. That's exactly what we have. And if we don't have the absolute values, we're not going to have an interval of convergence. Okay, because we have to have this less than 1, but then we're going to check the endpoints. We're going to check the endpoints to make sure that it's a less than symbol, or to make sure that we're including things when it could converge at a different value. Okay, like an endpoint. So let's go do that. So if we were to rewrite this, we get to add 2 to a -1, and we get 1. And we get to add 2 to 1, and we get 3. So we're going to check when x is equal to 1 and when x is equal to 3. So if we plug that into our sum, I kind of like to just bang this out and do this all at once. Wherever we see x, we're either going to put in 1 or we're going to put in 3. Okay. So now, if you take a look at our sum, this is just really the summation of 1 over n, okay, because 1 to the nth power is still going to be 1 no matter what we plug into that. Okay. And so if you remember, you know, p is 1, this is going to diverge. This is your harmonic series, by the way. This diverges. So we're not going to include the 1. Okay, so let's say 1 is less than x here. And let's go and finish this one down here with the 3. So we have -1 to the nth power. Now, like I was saying before, 1 to n is just going to be 1. So this is going to be our expression. Okay, so for the alternate series test, okay, we can take a look at trying to find if it converges or diverges. So for the alternate series test, we're going to take the limit of this expression, make sure it's equal to 0, and it is. And then we're going to also check to see if our n plus 1th term here is going to be less than or equal to our nth term based on the denominators. This is true. So this is converging. And we can now finish our interval and say that our interval of convergence for part A is from 1 to 3, not including the 1, but including the 3. And you can do this in interval notation as well. It's much easier to write. And the notation would be really nice, too. Okay, so for part B, f prime of x, that means we're going to take the derivative of our series. There's the prime. And so we're going to leave the summation the way that it is, with the infinity at the top, the n equals 1 at the bottom. Now, if you remember what I had said, okay, this is an n, and we're going to just affect where the x minus 2 is, where the x is. So, leave the negative 1 to the nth power, leave that it's over n, this whole thing. Now, just like we would use the power rule, we're going to move the n in front of the expression for x minus 2. We're going to subtract 1 from the n. So this is how we're taking the derivative of this particular series. Okay, and we're going to continue to simplify it so that way we can figure out the rest of the problem. Alright, so this right here is going to be, hopefully you can hear just me, f prime of x. Okay, so there's some people in the background. Hopefully you can hear just me. And we can proceed to find the interval of convergence for this. Now, since I already reviewed and went over the interval of convergence for part A, I'm just going to let you know what the interval of convergence is for part B here. Okay, it's from 1 to 3 exclusively. We're not including the 1 or the 3. Towards the end of the video, I'll walk through why that is. Okay, but I just want to make sure that the chunk of this video that you are watching is going over the new stuff. Like, we never took a derivative of a series before, and we never integrated that, so let's get to part C. Okay, so for part C, we're going to need to do is leave the sum, okay, have like the n equals 1 and the infinity there, just like you see it. But now, when we integrate, remember affecting where x minus 2 is. So we end up leaving the negative 1 to the nth power, leave the denominator of n, okay, we're going to add 1 to our exponent. So if you corrected that exponent, you're adding 1 to n, and we have to divide by our new exponent. So the denominator is going to look like this right here. You need to put parentheses, so you multiply the n with the quantity of n plus 1. Okay, now let's also review that it's an indefinite integral. So we do write a plus c. Okay, now you can write plus c after the series. Sometimes people get that a little bit confused with the series, so instead of putting it out there, you can actually add it to the front. That does not really matter. So we're able to integrate this. Okay, so now we need to know what the interval of convergence is for this particular series. And I could go through this at the end of the video. We already went through how to do that for part A, so let me tell you what it is for part C. It's from 1 to 3, and we're including both 1 and 3. It's inclusive. So there we have it. Okay, we're able to learn how to differentiate a series and integrate a series. Okay, so if you want to continue for the rest of this video, you can, as I show you how you get those intervals of convergence. But if you want to stop, you think you've got it, then you're good to go. Have a great time practicing your series. Thanks, and good luck. Okay, so we already found the interval of convergence for part A, so let's continue and find it for part B. So if we remember how we wrote the series for f prime of x, it was just negative 1 to the nth power times x minus 2 to the n minus 1 power. Now, if you remember how to find the interval of convergence being the limit, as n approaches infinity for the n plus 1th term. So I need to make sure that I include that in here. Before I actually do any sort of division. And I don't really have much of a complex fraction here. Okay, I do need to simplify a little bit, but as you kind of include, the expressions here, you can see it's a little bit easier to work with. Okay, so I just have to write it neater, and then it would be better for all of us. Okay, so just bear with me. Sorry about that. There we go. And, okay, so we have negative 1 to the first power, okay? And then we have the quantity of x minus 2 raised to the power of n plus, I was going to say plus 2, but it's actually n minus n plus 1. So it's just the first power. Okay, so we went through this before. This is just going to be 1 because it's the absolute value. And what we're going to have here, the limit of this expression, we're treating this as this minus a constant. So we could pull this out in front of the limit. And we're treating it as constant because it's as n approaches infinity. So if we factor that out, we'd end up with a 1. So it's just the absolute value of x minus 2. So we want that less than 1 in order for our series to converge. Okay, which means that we can add 2 to each one of these, and that's how we end up getting the 1 and the 3. So you're going to see it's a common theme because we already know the answer. It's 1 and 3 exclusively, so it kind of stays this way. But we want to know why. We got to always check our endpoints. All right, so let's do that. So we want to plug in 1 and plug in 3 into our summation. So remember, it's just that one expression, like negative 1 in the n power times x minus 2 to the n minus 1 power. So I left a little space for where the x is because we want to plug in a 1. And let's finish writing our summation. Okay, so now we're going to plug in 3 for x. Okay, remember we're subtracting there. So what did these simplify to? Okay, so this one is going to be negative 1 to the nth power. And we have a negative 1 in the n minus 1. Okay, so same base. And we're multiplying so we can add the exponents. So we end up getting the sum of negative 1 to the 2n minus 1 power. Okay, so we definitely have an alternating series here. Okay, but what we would do here is check it with the nth term test. This is going to diverge by the nth term test. Okay, so let's review the nth term test. Well, if we plug, that's a 2n minus 1. If we plug in okay, larger and larger values for n, it doesn't matter what they are, whether it be 100 or 101 or whatever that may be, your answer is going to be -1. And since this is not 0, okay, this is going to diverge. I'm going to squeeze it in. Hopefully you can see that. And that's why this is going to remain as less than 3. So let's take a look at our other summation. Okay, so this is where we're going to check our other endpoint. We don't need all of that. I just need some space. So, yep, here's my eraser. So here we go. All right, so if we simplify this, okay, we have -1 to the nth power, and we have 1 to the n minus 1 power. So if you take a look at this, okay, 1 to any power is going to be 1. So we really have just the summation of -1 to the nth power. And by the end term test once again, okay, we end up taking the limits of this expression, okay, as n approaches infinity. So you're going to end up getting not 0. Because even if you're thinking, okay, the answer is not always 1 or always -1, neither one of those answers is 0. Because this definitely diverges, and once again, we know that it's not going to be equal to 1. So that's why it remains as 1 to 3 exclusively. We're not including the 1 or 3 because those endpoints would make it diverge. So let's take a look at the last one, part C. Okay, so we already did these intervals of convergence, so let's do the last one. If you remember our answer from the last one, okay, we're going to focus on the part that is our sum, because we need to do the ratio test for that sum. So we want the absolute value of the n plus 1 for that sum, and this one is a fraction, so make sure you're looking at a pretty complex fraction here. So we want the nth plus 1th in the numerator, but there was also plus 1. So take your time to make sure that you write this out completely, and it makes all sense. Alright, so that's the numerator, and we need a denominator, and you can leave it as the nth term. Okay, so hopefully we can see all that. Alright, it looks pretty good. Okay, so we want this limit as n approaches infinity. Okay, so let's simplify this, and that way we can finish our ratio test. So let's do that. So we have the limit of what looks like -1 to the n plus 1 power over -1 to the nth power. And we have x minus 2 to the n plus 2 power, okay, over x minus 2 to the n plus 1 power, okay, and our denominator, okay, is n plus 1 times n plus 2, and if we do that keep, change, flip, our denominator becomes part of our numerator. It's n times the quantity of n plus 1. Okay, so there's an absolute value there. Hopefully we can kind of see the flow from one to the other, and let's keep simplifying. Okay, so I've already discussed this many times. This is going to be -1 to the first power, which is -1, but it's an absolute value, so this is just going to be 1. Okay, and over here what happens is that we have n plus 2 minus n minus 1, so it's just x minus 2 to the first power, okay? So that's pretty cool to kind of see that occur. And then the n plus 1s cancel. So you end up looking at n over n plus 2 as our expression in our absolute value. Okay, so we're treating this right here as our constant, and it's in an absolute value, so don't forget the absolute value sign. And even over here, keep the absolute value, but it is positive, and the degrees are the same. We can divide the leading coefficients. This is just going to be 1. And 1 times the absolute value of the quantity x minus 2 is just that. It's the absolute value of the quantity of x minus 2. So we want this to be less than 1 in order for this to converge by the ratio test. So let me write that out as right after I erase this. So here we have it. So our interval, once again, if we add 2 on both sides of our compound inequality, we get that x is between 1 and 3, but are we actually just keeping it as 1 and 3 exclusively, or are we including it? So it looks like we're including it, so let's see how that ended up happening. Okay, so when x is equal to 1, okay, we're going to actually plug it in where we saw that like c plus our sum. And don't worry about the c so much. Just remember that x became 1. And this is a plus sign. Sorry about that. I'm writing it, but it doesn't always come up on the iPad. Okay. So what happens is that this becomes c plus the sum. There's a plus missing. Please make sure you fix that. Negative 1 to the power of 2n plus 1 over n times the quantity of n plus 1. Okay, so if we take a look at, we're going to do the direct comparison test here. So if you look at our sum, and we need to have these in here, okay, I'm aware that the numerator is going to end up being negative 1 all the time, okay? But I want to compare 1 over n times n plus 1 with 1 over n squared. So we know what's going on with the sum of 1 over n squared, because this is a p series, and p is equal to 2, and 2 is greater than 1, so this is going to converge. Okay? And if this is the bigger one between these two fractions, and it is, then by direct comparison test, this is also going to converge. Now, you may be thinking, if there's a negative, then this is not going to work. Then it's actually the bigger one over on the left than the smaller one. But if you think about, instead of your two curves, bigger and smaller, if the big one converges, the small one converges. Same thing happens if you start to like flip them, okay? So your smaller function is going to be forced up to have smaller and smaller values. So it works whether you have like the negative or positive there. So it makes more sense with the positive, and that comparison makes it easier to do the direct comparison test and make sure it's convergent. So you know what? This endpoint is convergent, so we want to include it in the interval of convergence. So that's why we have a bracket, and that's where we're going to say that there is an equal sign over here, guys. So let's check the other endpoint. Let me erase this. Okay, so already start setting it up. We're going to check x equals 3. So remember, yeah, we had the constant, and we didn't really do anything with the constant. We're focusing on the sum part. That's okay, but it is part of what the this expression equals. So you should have it there. We're focused to see if this series converges or not. So replace the x with a 3. Okay, so hopefully you have this answer somewhere. The same one we used for the last time, except we're not putting in a 1, we're putting in a 3. Okay, so hopefully you have that all and it's all clear, makes sense. And let's keep going. Let's simplify this so we know what sum we're looking at here. So we still have a negative 1 to the nth power. Now we have 1 to the n plus 1 power, and we know that's just going to be 1. So we're looking at a denominator of n times the quantity of n plus 1. Okay. So a very weird thing happened when I was writing that out. The page just went back to what I was doing last time, but that's okay, because we can still kind of continue by plugging in 3 and taking a look at our series. So now, we can actually, in this case, where the numerator is either negative 1 or positive 1, use the alternating series test. Okay. So that's good. We could kind of review the alternating series test. So this being our alternator, okay, a sub n is going to be 1 over n times the quantity of n plus 1. And I need some space. So the limit of this expression, okay, is going to be 0. Because we have like 1 over n squared, okay, it's like c over x to the r power. All right, so this is going to be 0. So that's the first thing that we need to have for an alternating series. And next thing we need to do is plug in the n plus 1 and see if one was greater than the other. So I'm trying to do that. And if I do n plus 1, I'm just going to simplify it already to be n plus 2. All right, so we know this is going to have more terms in the denominator. So this is definitely going to be less than a sub n. And this means that our series is convergent. Okay, so not only was one side convergent, but this side is, and that's why there's going to be an equal sign as well at that endpoint, and we're done. We went through all of them, and we got to review a lot of the different tests in Unit 10, as well as integrating and differentiating. I hope you had such a great time with this course, and as happy as it made me, I hope you guys are happy. Good luck with everything. All right, good luck and have fun. Bye, guys.